In the past few decades, differential equation-based methods have become extremely popular because of their ease of implementation and the efficient use of memory. We can cast all numerical solutions to Maxwell equation into solving an equivalent matrix equation. So for the differential equation-based method, these equivalent matrices are sparse. Also, there is a distinct difference between differential equation solver and the integral equation solver. In differential equation solver, we solve them for the field that spreads throughout all of the space. And in contrast, in the integral equation solver, we solve for the sources. So for surface scattering phenomena, the equivalent currents resides on the surface or at the interface between regions. We effectively reduce the dimensionality of the problem. And because of this, the known count in integral equation solver can be much smaller than the unknown count in differential equation solver, or problem of equivalent size and wavelengths. In contrast, the integral equation-based method gives rise to a smaller number of unknowns. The method is also very multifunctional and convenient for handling sophisticated geometry. So on the one hand, the integral equation method produces dense matrices that are expensive to store and solve. And on the other hand, the recent progress in fast solvers for integral equation has opened new horizons. So in particular, the researchers developed efficient integral equation method that did not previously exist. So let us briefly consider the case of the finite difference time domain method. And this technique is considered to be matrix-free and mesh-free. We use this terminology because we can generate equivalent matrix vector product with some very simple computer operations, and mesh is rectilinear, and we do not need to store it during the computation. So furthermore, this finite difference method is considered an optimal algorithm in a sense that it generates order of n power alpha numbers with order of n power alpha operations. So as a consequence, LDTD has become extremely popular. And this is there is a large class of computational problems where we need to mimic an infinite space. So obviously the computer has only a finite amount of computational resources, and differential equation solver requires the use of absorbent boundary condition. This absorbent boundary condition can mimic the radiation condition at infinity. A recent progress in developing computational technique for perfectly matched layer has stimulated much activities in this area. So in this approach, we aim at efficient absorption of the radiation that goes into infinity. And in contrast, we can derive an integral equation with Green's function, and they already satisfy the radiation condition. So in other words, the integral equation provides a solution that already satisfy boundary condition. An alternative way to infer the radiation condition in differential equation solver is to truncate the solution region with boundary integrals. So those boundary integrals in turn are solved with integral equations. Let's first focus on solving differential equations. In this case, we construct a numerical grid, and we consider fields propagating on this grid. In other words, if a field propagates from point A to point B, we target those fields on a numerical grid. In this mode of field propagation, a smaller error is often committed, resulting in a phase error in the field. So the problem is that this space error is cumulative and it becomes larger with a larger simulation size. Uh, Consequently, we have to increase the grid density to mitigate this error. And therefore, a larger problem size, a higher grid density required in different equation solver. So it's important to understand that there are two separate issues. One is that we increase the domain size, and that directly increases the computational resources. And the second one is that we also have to increase the grid density to reduce the error. So this means that demand for the resources increases faster than simply increase in the computational domain. And in contrast, an integral equation solver propagates field from point A to point B, and for that, it uses an exact closed form Green's function. And therefore, the problem of grid dispersion error is often less severe in integral equations.